All right, let's plow through some more gas laws. I love gas laws because they make sense. Like if you think about gas particles on a particle level, you can kind of interpret the meaning of these gas laws. You can predict what should happen as a result of a calculation. Graham's law of effusion is no different. So a little bit of vocab here. Now you probably heard of the word diffusion. Diffusion is just the general movement of particles from an area of high concentration to low concentration. So I could put a drop of food coloring in water, and we would say that eventually the food coloring diffuses through the water. It moves from high concentration to low concentration until it's evenly mixed. I could say I have a can of air freshener and I squirt some in the front of the room. Well, eventually that concentrated air freshener will diffuse throughout the room until it's evenly distributed. Okay, so a very general term. Evenly distributed might represent a state of what we call equilibrium, where the particles are equally dispersed. Effusion adds just one little qualifier. The particles are still moving from an area of high concentration to low concentration, but they are moving through a small opening. So now specifically, I'm not talking about like, I have a balloon full of smelly gas, and I pop the balloon, and the gas particles immediately disperse throughout the room from high concentration to low concentration. This is more of like, I have a pinhole leak in my balloon, and slowly the particles will effuse through this tiny opening where they're highly concentrated in the balloon, and eventually they'll all leave the balloon and become evenly distributed throughout the room or whatever the space might be. So kind of like this picture on the bottom that's showing high concentration of particles, low concentration of particles. Well, eventually the particles want to be evenly distributed throughout this contraption, but they're moving through this tiny little hole from high concentration to low. So again, it's like a pinhole leak in a balloon, or maybe like an aerosol container, or like a butane lighter, where there's a small opening by which these particles are moving from high concentration to low. Now, the description of Graham's law sounds a little bit crazy, but it actually makes perfect sense. At the same temperature and pressure, the rate by which two gases will effuse through an opening is inversely proportionate to the square root of their masses. Ugh, kind of a mouthful. Okay, so let's break it down. The rate by which two gases will effuse through an opening. So rate is like the speed. How fast are these particles moving through this tiny opening? Rate will be measured in meters per second. Kind of like the speed. How fast are the particles moving? That rate by which these gases move through a tiny opening is inversely proportionate to the square root of their mass. Okay, well, inversely proportionate means that if I increase one variable, the other one decreases. And then it's somehow like rate is inversely proportionate to the mass. Mass, in this case, is going to represent molar mass. What we find on the periodic table. So we measure grams per mole. Inversely proportionate. The rate is inversely proportionate to the mass. Okay, so in other words, let's say I have a massive particle with a large mass. Inversely proportionate means then that the other variable would be low. A massive particle A large particle with a large mass travels slow. A small particle with less mass travels at a higher rate. Oh my gosh, this is common sense. If a gas particle is heavier, if it has a high mass, it travels at a slow rate. It moves slower. Wow. Oh my gosh, this makes sense. Now, by saying inversely proportionate, our equation looks kind of like another inversely proportionate relationship that we've looked at in the past. Boyle's law. If you increase the pressure, you decrease the volume, where it was a multiplication. This looks real similar. I'm going to give you that. That'll be on the next test. R1, and it is the square root of the mass. R1 times square root of M1 equals R2 times square root of M2. So R1 will represent the rate of an initial particle. We're going to compare two particles. Times the square root of the mass, which we're just going to get on the periodic table, the molar mass, equals R2 times square root of M2. So this will be the rate and the mass of a second particle. We're going to compare two different gases. The larger the mass, the slower its rate. Oh my gosh. And again, it's plug and chug. This is great. So some examples. Okay, anytime you see this rate data, like this meters per second, this is your only choice. R1 times square root of M1 equals R2 times square root of M2. It's the only equation that has rates. So anytime you see speeds, meters per second, this is it. Okay, given that neon gas travels at a rate of 400 meters per second at a given temperature, calculate the rate of effusion for butane at that same temperature. Okay, so we do have to compare these gases under the same conditions. So they have to be at the same temperature and pressure. I mean, I could have like a heavy particle and a lighter particle, but if I increase the temperature of the heavy particle, well, then that particle has more kinetic energy, and maybe I can make it move at the same speed as a smaller particle. So we compare these different gases under the same temperature and pressure. Now, it does not matter what gas you call gas 1 or gas 2. We're comparing neon and butane, but honestly, it doesn't matter what gas is 1 or 2. I don't know, neon comes first, so maybe I'll call neon gas 1. Okay, so R1 is going to be the rate of effusion for the neon, which is 400 meters per second times square root of its mass. It comes off the periodic table. So you just look up neon with a reasonable amount of sig figs, maybe like 2 decimal spots. 20.18. You could say grams, it's molar mass, so it is grams per mole. Equals R2. Calculate the rate of effusion for butane. So that's what I'm looking for. R2 times square root of M2. Now, if you didn't know, I would tell you the formula of butane. Butane is C4H10. We're going to do a lab with some butane. C4H10. All right, so you really just plug it in on your calculator. Carbon, 12.01 times 4 plus 10 hydrogen. And we're right around 58. So we'll go 2 sig figs. 58.14 grams per mole. I don't need to see work for that, just add it up. I mean, I would tell you the formula if it's something that you weren't familiar with. These masses come from the periodic table. So don't freak out if you don't see like mass data. It's on the periodic table, which you'll have. And now you honestly just put this in your calculator. 400 times the square root of the 20.18 divided by the square root of my 58.14. Cool. Okay, so I get a rate. For sig figs, I usually just kind of leave something similar to the original. The first rate had 3. There's a decimal at the end of those zeros. So let's leave this as 236 meters per second. So this would be the rate at which a butane molecule would travel under the same conditions. Now, we don't need to know the temperature and the pressure. We just need to know that they're the same. You can check to see if this answer is reasonable. The butane is more massive than the neon. There's the molar mass of the neon. The mass is greater, so the rate should be lower. A heavier particle moves slower. Oh yeah, this makes sense. It's got to be something less than 400. It's moving slower. Oh, cool. So I like this gas law stuff. I mean, number one, the math is easy. It's just algebra. But then number two, I like being able to look at my answer and at least evaluate it to see if it makes sense. Did I make a mistake on my calculator? Is my answer reasonable? Yeah. Gosh, this is great. Okay, so we could solve for a rate. We could solve for a molar mass. A carbon monoxide molecule travels at a rate of 409 meters per second at room temperature. What is the molar mass of a molecule that travels 322 meters per second at the same temperature? Cool. Let's plug it in. So here's my equation. For all of these, obviously, this is my equation, but in general, it's the only one that has rate. Okay, so it doesn't matter if I use carbon monoxide as gas 1 or gas 2. It comes first, so I guess I'll just make it gas 1. Its rate is 409 meters per second. And I know it's carbon monoxide, so I can go square root of its mass. I got carbon plus oxygen, 28.01. And molar masses, 2 sig figs are plenty. That's the carbon monoxide. This time I know the rate of the second particle. So the second particle travels 322 meters per second under the same conditions, but never do they tell me the identity of the particle. And so the best we can do is to solve for its mass, which is going to be square root of the mass, square root of m2. Okay, so common error. People are on autopilot. They're like, gosh, this is so easy. I just plug it in my calculator. Out comes the answer and I'm done. So they plug this in. 409 times the square root of the 28.01 divided by the 322. Cool. And they're like, okay, mass equals, let's see, maybe like 2 decimal spots, 6.72, done. Maybe they even put like a gram or something behind it. Done. 6.72, that's what my calculator says. Hold on. Let's see if that even makes sense. The second particle travels slower than the carbon monoxide. Well, if it travels slower, that must mean that it's more massive. It must have a larger mass than the carbon monoxide. The carbon monoxide's mass was 28 grams per mole. This doesn't even make sense. This mass needs to be greater than the 6.72. And now maybe you're like itching right now because you see what the common mistake is, right? What you actually solve for is square root. Square root of the mass equals the 6.72. So to get the true molar mass, to get rid of that square root, you got it, we need to square both sides. So the real molar mass is not the 6.72. I like this better. Oh, whoopsie, 45. And again, maybe we'll go 2 decimal spots on our molar masses. 45.19 grams per mole. That makes more sense, right? The particle has to be more massive if it travels slower. So I need a molar mass that's greater than the 28. Love it. Now, I don't know the identity of the gas. I mean, this gas, it could be anything. I mean, maybe they would say something like, this is an unknown diatomic gas, or this is an unknown noble gas. And if you could solve for this bad boy right here, this molar mass, then you could go to your periodic table and match it up and identify the gas. Now, this one is, I don't know, some random gas. But if they were to give you a little hint that this is a diatomic gas or it's a noble gas or something like that, then this molar mass should match up on the periodic table. Okay, so a real common mistake. And of course, if this were multiple choice, the 6.72, that's one of the choices. But it's not going to trick you. All right, and then here's one other twist. An unknown gas effuses through an opening at a rate of 3.53 meters per second. A sample of nitrogen gas under the same conditions effuses 3 times faster. What is the molar mass of the unknown gas? Okay, so it's similar to this carbon monoxide one, right? We're solving for the molar mass. So I've got an unknown gas and I've got nitrogen gas. And it really doesn't matter what gas you call gas 1 or gas 2. It really doesn't matter. So, I mean, if you really want, the unknown gas comes first. And I do know its rate. The unknown gas has a rate of 3.53 meters per second. But I don't know its molar mass. What is the molar mass of the unknown gas? Okay, so we'll say square root of M1 is my variable. And it really wouldn't matter if you made this M2. It could be gas 2. It doesn't matter. Okay, so the second gas is nitrogen. They don't specifically come out and tell me its rate. But they tell me that it effuses 3 times faster. Oh, brother. I'll just multiply the original times 3. So 3.53 times 3. Oh my gosh, I can do it. So this guy, let's call it about 10.6. 10.6, I'll go 3 sig figs. Meters per second for the nitrogen. And now here's another common mistake. Okay, I'm going square root of M2, which is nitrogen. Diatomic. It's nitrogen gas. So you'd have to be a little bit careful of your diatomics anytime they're referring to a molar mass. If you're going to need the molar mass, then if it's diatomic, you do have to multiply by 2. So instead of 14.01-ish, I'm going to go 28.02 grams per mole. Okay, so now we just plug it in and this should be a breeze, right? Okay, so let's start with the 10.6 times the square root, 28.02, divided by the 3.53. All right, so again, this isn't going to catch you. What we're really solving for is the square root of M1 has about 15.9-ish. Yeah, like 90. But to get the true molar mass, I need to get rid of that square root. So I need to square both sides. Not a big deal. M1 is about, oh boy, 252. And if I'm going like 2 decimal spots on my molar mass, like 66 grams per mole. Something like that. And again, I'm not like super picky on sig figs, as long as it's something reasonable. I mean, like my calculator has the entire screen full of decimal spots. I don't want to see that. Something that I could really measure in the lab. Cool. So yeah, if this unknown particle moves substantially slower, it should be substantially more massive. Now, there's another question that I'm thinking of that's very similar to this, but it doesn't even give you the 3.53. It just says, hey, I've got this unknown gas that moves through a small opening. A sample of nitrogen moves 3 times faster. What's the molar mass of the unknown gas? It gives you like no specific rate. It just says that one particle moves 3 times faster than the other. You know what? It really doesn't matter what the specific rate was. You can make up whatever you want. If you did this calculation, as long as the nitrogen moves 3 times faster than the unknown gas, your calculations are going to come out to be exactly the same. It really doesn't matter what the specific rate is, as long as you keep the proportion the same. So if they would have just said that one gas moves 3 times faster than the other, and they don't give you any specifics, make up whatever you want. I mean, you really do anything you want. You could make this like, I don't know, 10 meters per second, and you could make this 30 meters per second. You could go 1 and 3. You could go 100 and 300. You could make up anything as long as one gas went 3 times faster than the other. Your calculations will come out exactly the same. So there's one that's like popping in my mind. I don't remember where you're going to see it, but you will. And sometimes people get a little stumped because they're like, well, I don't even know what the original rate is. I know the other one's 3 times faster. Doesn't matter. Be creative. Make up whatever you want. But here's another great gas law. Simple math. And it just makes sense on a particle level. The more massive the particle, the slower it's going to move.